Hi, welcome to the IMechE Tribology webinar series. So this webinar series has been running since October 2023 and it offers an opportunity for postgraduate students to present their work and interact with other researchers working in the field of tribology. So far we've had presentations that have covered a range of areas in tribology, from wind turbines to rail and also biotribology, and today we'll be hearing about additive manufacturing. So questions and interaction with our speakers is really encouraged as part of this series, and we'd love you to ask questions throughout the presentation. You can do that through the Ask a Question box, and then at the end of the presentation I'll be able to put those to Kieran. So today we've just got one speaker, so I'd like to introduce you to Kieran Narr from the University of Sheffield. So Kieran's a final year PhD researcher. He's investigating friction and wear properties of additively manufactured polymer components. And he's been working with the Advanced Polymer Sintering Lab and the Leonardo Tribology Centre. And that's to consolidate the knowledge between both additive manufacturing and tribology. So we've got a really interesting presentation. And with that, I'll hand over to Kieran. Thank you.
Great, thanks, Kate. I'll just get my slides up now. Amazing. So yes, thanks, Kate, for the introduction, and thanks very much to the IMechE for facilitating this talk and facilitating the PGR Tribology Group webinar series more generally. I've managed to catch most of the previous talks, and it's been really great hearing about all of the varied and interesting work being carried out across the country. So as Kate mentioned, and I guess this title suggests, my talk today aims to provide some insight into my PhD project, which focuses on investigating the tribology of laser-sintered polymer components. Now, the official and maybe more descriptive title of my PhD research is investigating the surface friction and wear properties of polymer laser-sintered components. Though if you've seen anything that I've outputted at conferences in the past, you'll know that I much prefer to lead this with this slightly more fun title, so Polymer Laser Sintering, Fact or Friction. So I guess, as you've managed to gather from my free title slides, my work aims to consolidate knowledge between polymer laser sintering and the field of tribology. And it would be remiss of me not to shout out my two fantastic supervisors. So that's Candice and Roger, who have been fundamental to this work. Candice leads the Advanced Polymer Laser Sintering, our Polymer Sintering Lab at the University of Sheffield. And it's been great in working with her alongside Wendy, Kurt and Ryan on all things Polymer AM. And a special mention to Roger, who must be an IMechE VIP at this point. He supported the tribology side of this project alongside with other members of the Leonardo Tribology Centre. So I guess before jumping straight into tribology, I just want to give a quick overview of the polymer AM landscape, so you can see how laser sintering sits with respect to other AM technologies that you might be aware of. So I guess naturally when we first see or hear the word additive manufacturing, we tend to think 3D printing. And at the time of creating this PowerPoint, I Googled both the terms, both 3D printing and additive manufacturing, and found that 3D printing yielded around 10 times more search results than additive manufacturing. So definitely more ubiquitous within common vocabulary. Though I think the important takeaway message when referring to these technologies as either additive manufacturing or 3D printing is that they are much more than just one technique. In fact, additive manufacturing technologies are typically classified into seven general categories, as you can see on the screen, with each often comprising of many more specific techniques. And when we look at how additive manufacturing is typically being used, you might also be interested to learn that additive manufacturing is primarily being adopted to manufacture end-use components, so has advanced from just being a tool for, let's say, prototyping. And I should mention this data has been taken from the Wohlers report, which is a document that gets published annually and collates insight into every aspect of additive manufacturing that you can think of. So additionally, if we look at how the additive manufacturing materials market is segmented, we can see that polymer powders are the most widely adopted. And if we zoom into this a little bit more, we see that one material reigns supreme, and that is nylon 12, otherwise known as polyamide 12. And this is the polymer that almost all of my work has been centered on, and will be in reference to throughout the rest of this talk. But ultimately, if we collate insight gained from the previous two pie charts, we can see that polymer additive manufacturing methods, in particularly powder bed fusion processes, are the ones that are most widely adopted for producing functional components for end-use applications. And this provides great context for me because, as I've hopefully managed to convey by now, my work focuses primarily on the polymer laser sintering process. Now, this GIF summarizes the process really well, but just to break down the build process, the laser sintering build process, into its constituent elements. First, powder, which in my case was nylon 12, gets deposited across the build layer by some form of recoating device, which in this case looks to be a roller. Secondly, a laser or multiple lasers selectively melt regions of the powder bed in accordance with the sliced CAD file. The build plate then gets lowered by a distance equal to the desired layer thickness of the parts being produced. And then this process gets repeated until every layer or slice of every part within the build has been sintered. So we're building parts up vertically throughout the build volume. And these are just some parts that I found in our display cabinet in the lab. But as you can see, they do a great job of demonstrating some of the highly complex and intricate support structures that we can produce. I should mention that this technique is somewhat unique because during building, the surrounding powder supports overhanging features, which means that we don't need to include support structures. Also, this allows us to be able to build assemblies, and the nylon 12 parts that we typically produce have strengths and stiffnesses akin to those of parts built via injection molding. However, if laser sintering is as great as I've made it out to sound so far, what's the issue? Well, when we look at the challenges companies report when looking to adopt additive manufacturing technologies in general, we learn that part quality is one of the most significant hindrances to its adoption. And I guess this is where tribology comes in. So if we can better characterize the functional performance of laser sintered components, that should enable us, that should enable companies to best assess their suitability for their intended use functions. So I think it's worth just quickly giving a quick introduction to the science of tribology. And as defined by the IMechE, tribology is the science and engineering of surfaces in relative motion and encompasses the major topics of friction, wear, and lubrication. Now, I'm sure all of the tribologists listening along will agree that it's slightly cheesy, but at the same time, very true to say that tribology is well and truly really around us. Some classical examples include the interactions that maybe occur in our engines or at the rail wheel interface on the trains we take to get into work. But some also less obvious examples of tribology include the grip that climbers and boulderers feel when scaling rock faces. If you want to know more about that, talk to Kate. Or the interaction that occurs in our mouths, which explains why chocolate tastes so good, which I guess is something I'm well practiced at. And other daily routine activities like the science behind what happens when we brush our teeth. And more recently, I realized that tribology is not only limited to the real world. If anyone's ever played Mario Kart, you can blame tribology for the frustration that you might feel when you get hit with a banana skin mid-race. So there you go. And those fundamental aspects provide a nice framework for my research. And I want to talk about what I've learned about each of them in a little bit more detail throughout the rest of this talk. So starting with surfaces. Now this picture almost looks fictional. It's like it could be an image taken from a Mars rover or even a landscape from the new Dune film, I guess. But this is actually a laser sintered nylon 12 surface that I captured in the lab. And as you can see up close, they are incredibly characteristic, which I'll get into the details of in the next few slides. But just to draw attention to the fact that these surfaces are just consolidated powder particles at the end of the day, I've included this SEM micrograph, which for comparison really isn't that dissimilar just to a zoomed in black and white photo of a bowl of Rice Krispies. Now, the first experimental package of work that I undertook when beginning my PhD was to characterize the roughness of laser sintered nylon 12 surfaces. Though when setting out to do so, I quickly discovered that there is way more to roughness than just one value. In fact, there are over 55 different ways to describe surface roughness. But the two that I determined that were most apt for my work was root mean square roughness and skewness. So I imagine quite a lot of you are familiar with the term RMS roughness, but for those who might not be as well acquainted, RMS roughness tells you information about the height of a surface being evaluated. Skewness, on the other hand, is an amplitude density function, so which tells you information about the symmetry of the surface being evaluated, and more generally indicates whether it is the surface being evaluated is asperity peak or valley dominated, as illustrated, or neither. And what we found when evaluating the top and bottom surfaces of cube-shaped specimens were as follows. So before I get into the numbers, I guess these scan images qualitatively describe each surface, and I'm sure you'll agree there are no marked visible differences between them. And similarly, when we look at their resultant RMS or SQ roughnesses, we discovered that their surface heights typically vary by the same magnitudes. But things got interested when we started to compare their skewness values. So yeah, the one clear and obvious trend that we did manage to see was that the skewness values of top surfaces were almost always positive, so greater than 0, which meant that these resultant top surfaces were asperity peak dominated, whereas the skewness values of bottom surfaces of samples produced typically were centered around 0, which meant that they were relatively Gaussian, and therefore neither featureful of peaks nor valleys. So this naturally prompted the question as to why are laser sintered top surfaces characteristically peak dominated? And it took a few weeks for me to come up with any form of idea or hypothesis. But when I did come up with an idea, it was kind of like having one of those eureka moments. So if we refer back to our GIF of the laser sintering build process, we know that laser sintering is essentially a process that involves consecutively depositing and sintering layers of polymer powdered material until we produce all our parts vertically. Though one part of the build process that we weren't able to grasp from this GIF was that upon the final build layer being sintered, it's common practice to then consecutively deposit numerous more blank powder layers, otherwise known as finish layers, on top of the parts produced. And on our machine, for example, it's default practice to deposit 40 additional finish layers on top of the parts. And the reason for this is to bury all the parts produced to ensure that they subsequently cool evenly, to prevent them from warping. Though, as you can see from this illustration, this is also the mechanism that I thought might be the reason why resultant top surfaces tended to be asperity peak dominated. And there was a really straightforward way for me to validate this experimentally, and that was to build more samples and make sure to hit the stop button on the machine as soon as the final build layer had been sintered, to prevent any additional finish layers from being, any finish layers at all from being subsequently deposited. And as you can see, there was a drastic difference between top surfaces built with and without finish layers. The latter were instead found to be pore dominated, which you can kind of make out on the screen, and the resultant surface heights, I'm sure you all agree, was significantly reduced. Though this discovery then did go on to prompt a new question of what is the maximum extent by which we can reduce the top surface heights of parts produced with what we now know. And to do that, we executed a design of experiments to determine the influence that different laser parameters, specifically laser power, beam spacing, and scan speed, had on both RMS roughness and skewness, so the surface heights of parts produced and the symmetry of the parts that we produce. And these were the parameters that we used to do so. And we found some interesting relationships, which I don't want to go into too much detail about now, but one of the interesting takeaways was that after performing some statistical analysis, we were able to determine that beam spacing was the laser parameter that influenced top surface RMS roughness and skewness most significantly. And we attributed this to this mechanism, this double in situ laser scanning type mechanism that occurs when you employ laser beam spacings that are less than the radius of the laser beam. So we found that with lower laser beams, so 0.2 millimeters in our case, we had this double scanning effect, whereas when we employed standard laser parameters, so employing a laser beam spacing of 0.25 millimeters, we only partially had this double in situ scanning. And ultimately, we found that employing optimized laser parameters, we were able to reduce SQ roughness by 31%. Though to put this into perspective, when we instead build without finish layers, we managed to get reductions in SQ roughness of up to 48%. And finally, when we combo both of these mechanisms, so employ optimized laser parameters and build without finish layers, we found that it was possible to get reductions in top surface SQ roughness of up to 56%. And these scan images show the same findings, but visually, which I think highlights the magnitudes of these reductions really nicely. Cool. So that was a quick run through on laser sintered surfaces, focusing primarily on top surfaces. Now I want to just quickly share how these surface topographies affect their resultant part sliding behaviors. So to do that, we employed a lab-based tribometer, which allowed us to execute various different ball on flat rotational pin on disc unidirectional sliding tests, which, as you can gather, is quite a mouthful. But just to break this down, we chose to utilize a ball on flat configuration so that we get point contacts, primaries to avoid any misalignment issues, which are more typical with flat on flat contacts. And the rest of that term just refers to describes the way the test was set up, as shown in this photo. But if you aren't too familiar with tribology test methods, this one is akin to a record player, where I guess our polymer laser sintered disc samples were our vinyls, and they rotated relative to the pin or the needle in the context of a record player. So the first sliding related study that I performed focused primarily on the running in behaviors of laser sintered nylon 12 top and bottom surfaces. So this was to establish what happens when these surfaces are first subject to dynamic contact. And as you can see, multiple tests were performed at 3 different normal loads, so 10, 15, and 20 newtons. And what we discovered might seem quite obvious now, but top surfaces, which we previously identified as being asperity peak dominated, experience greater magnitudes of wear than bottom surfaces, which we found to be relatively Gaussian during initial sliding. So because these top surfaces were asperity peak dominated, they incurred greater amounts of asperity peak fracture and wear in general during running, as represented by the steeper curves in this figure. Additionally, when we looked at the resultant friction data recording during testing of both the top and bottom surfaces, we saw that over the first 20 meters of sliding, each surface exhibited different friction responses. So just to illustrate that a little bit more clearly, top surfaces exhibited this heightened transient friction response, whereas bottom surfaces exhibited these more classical plateauing increases in friction. And this suggests that these parabolic surges in friction recorded during initial top sliding, so the responses in blue, were caused by the presence of these additional asperity peaks, which provided augmented levels of resistance to sliding prior to them fracturing or yielding. And this was also confirmed via some scratch testing analysis we did, and this involved scratching different nylon 12 top and bottom surfaces, but instead of applying a constant normal load, we instead applied a progressive load from 0 to 50 newtons, just like so. And this animation shows the data collected during each scratch. So, and similarly to before, we can see that during initial sliding, top surfaces experience these heightened friction responses relative to bottom surfaces. And as the test progressed, we saw that these scratch coefficient of friction responses became more and more similar. This indicates that from a friction perspective, that the transition from transient to steady state sliding occurs when the penetration depth of the indenter also transitions from surface to subsurface ploughing. We also looked at the sliding behaviors of laser sintered components over longer sliding distances to investigate the friction and wear behaviors exhibited during steady state sliding, which, as illustrated below, which as the illustration shows, we executed sliding tests at low and high normal loads, sliding speeds, as well as converse contact configurations, but I'll cover that last bit in a few slides' time. And as you can imagine from this package of work, we collated masses and masses of experimental data, but due to time and I guess concentration limits, particularly my own, I'm just going to focus on the key findings. So this matrix shows the mean coefficient of friction responses recorded during each sliding condition. And almost immediately, the first thing you'll notice is the differences in variation in sliding exhibited during each sliding condition, particularly based on load. And I should have mentioned that this study focused on top surfaces specifically. So as you can see in the circle regions, we again saw these initially heightened running friction responses, though this was less apparent for 0.5 meter per second sliding, so higher speed sliding, which suggests that this mechanism is a function of sliding speed. Though focusing back on the contrasting variations in sliding, we're able to attribute this to the mechanisms by which each normal load was supported during testing. So the 30 Newton applied normal loads, which is our high load test condition, we found were supported by plastically deformed bulk surface material, whereas our low loads, so 3 newtons in this case, were supported by polymer surface asperities and partially yielded peaks. And as I mentioned earlier, we also carried out this testing procedure via converse contact configurations. So I've just spoken about metal pin on polymer disc testing, but we also executed these tests on polymer pin on metal disc via polymer pin on metal disc configuration. And the main difference between these contact configurations, which is mentioned in the figure, was the continuousness to which the polymer regions were subjected to dynamic contact during testing. So as shown in these images, during metal pin on polymer disc sliding, discrete regions of the polymer disc were only subject to dynamic contact for 1 instance per revolution, whereas during polymer pin on metal disc sliding, the polymer pin was always subject to dynamic contact during testing. So if we look at the results recorded for polymer pin on metal disc sliding, we instantly see these steady increases in coefficient of friction. And this was due to the buildup of frictional heat during testing, which led to thermal softening and subsequent enlargements in contact area. Perfect. So I just want to finish on what I think is a really interesting part of this project in general, and is a potential sort of opportunity to explore various other avenues of related research. And that's to explore the potential of modifying the friction and wear properties of laser sintered polymer components by including functional additives. So one investigation we did was exploring whether we can include solid lubricants within feedstock nylon 12 powders to modify, or in our intended hope was to reduce the friction and wear properties of laser sintered components, which is exactly what we went about doing. So more specifically, we individually included 3 different solid lubricants. So they were PTFE, graphite, and molybdenum disulfide into 3 different nylon 12 powders in 1% weight loadings, and incorporated them into the nylon powders by a very straightforward method of rotary tumbling or rotary blending, as you can see. And as these SEM micrographs indicate, which might be a little bit difficult to see on your screens, but we were able to identify that these solid lubricants were actually in the nylon 12 matrices we were evaluating, and qualitatively the results showed that these solid lubricants were well dispersed and showed very little signs of agglomeration. So just like before, we performed some ball and flat unidirectional rotational pin on disc sliding tests, which does not get easier to say out loud, on parts produced from each material. And what we found when looking at the friction responses was that PTFE was the only solid lubricant addition in which we saw significant modifications in friction. So this is that coefficient of friction trace just blown up a little bit, and I'm sure you're all wondering what's going on with that big spike in friction. Well, the consistency in which PTFE PA12's lubricating response broke down, both in terms of applied normal load and moment occurrence, suggests that this material's experienced a frictional heating related failure. So it's likely that resultant thermal softening led to the steel counterface further indenting the PTFE PA12 surface, which will have meant that greater ploughing will have ensued, and as a result, greater friction will have increased. However, prior to this spike in friction, we found that the addition of PTFE reduced coefficient of friction by as much as 37% and 50% during 10 and 30 Newton sliding, which we attributed to the formation of a lubricating transfer film, which is very characteristic of PTFE. And when we look at the wear results collected, we found the opposite to be true. So the addition of PTFE increased our wear rate. Our wear rates recorded, whereas the addition of graphite and molybdenum disulfide rather significantly reduced the amount of wear incurred during sliding. And we found this to be linked to the mechanical properties of the parts produced, specifically strength and stiffness. So to put that into perspective for you, the addition of PTFE reduced friction by as much as 50%, but ultimately increased the amount of wear incurred during sliding, whereas the individual inclusions of graphite and molybdenum disulfide had no notable effects on friction, but did significantly improve wear resistance. And this was all relative to unfilled laser sintered nylon 12. Perfect. So that's a quick run through of 3 years of PhD work in around 30 minutes, covering aspects related to surface, friction, wear, and lubrication. And whilst talking, I've just realised this is probably the last presentation that I'll give on as part of my PhD. So thanks for listening, and I'd be very happy to answer any questions that you might have. Thank you.
Hi, Karen. Can you hear me again?
Yes.
Yes, excellent. That's great. Thank you so much for your presentation. That's really interesting. And yeah, what a way to end your PhD journey with that fantastic way of disseminating your research. So we've had a good amount of questions in so far. If you have any more questions whilst you're still listening, please pop them into the Ask a Question box and we can add those to the list to ask Kieran. So I'm going to start with one of the questions we've got in already. It said, did you look at the dependence of roughness parameters on process parameters of the build process?
Yes, we did. We did. I didn't explicitly mention that, but we did look at how so different laser parameters, beam spacing, laser power, scan speed affected SQ and skewness roughness, which, as I mentioned, we also did look at how the effect of material reuse affected roughness parameters. So we looked at differences between virgin nylon 12 and nylon 12 with a refresh ratio of 50% affected the roughness of parts produced. But yeah, we primarily focused on laser parameters rather than things related to powder properties.
And that led to sort of an optimal laser parameter.
Yeah, again, we completed a design of experiments which allowed us to see for parameters that we chose to vary these laser parameters by an optimized set of laser parameters, which we found did significantly reduce SQ roughness, so top surface heights.
That's lovely. Thank you. Still on the topic of roughness, got a question in that says, how do you determine the zero line of a surface? I.e., what are you referencing off when you measure the height of a peak or the depth of a valley?
Oh, that's a good question, and I'm not sure I quite know the specifics of that off the top of my head, but we used an Alicona infinite focus microscope, and that gave us information into all things surface topography and roughness, and that did show where how the mean line was calculated, but I can't remember the specifics of how that was calculated.
No problem, thank you. That's just an interesting question really on surface roughness and sort of using the Alicona. I've used it gives lots of different roughness parameters. So I'll kind of add my own cheeky questions on here. How do you decide which of those roughness parameters to look at and which ones to ignore? And how did you decide what sample size to take your roughness measurement over?
Yeah, so yeah, like you said, the Alicona can output so many different parameters. So a lot of the parameter, so yeah, a large part of the decision we made to choose skewness and RMS roughness in particular was based on work that we'd seen in previous literature, and skewness gives you a nice image of symmetry of a surface, so it gives you a little bit of indication to its shape, whereas RMS roughness gives you information to its height, so I guess size or amplitude. And we thought having one parameter that does either would give you a pretty good description of a surface rather than just focusing on SQ or SA, which is pretty typical. But we did look at kurtosis. We looked at the maximum peak to valley height, that sort of thing. If I had more time, I'd love to look at more sort of hybrid parameters as well. So yeah, I guess it's a bit of a rabbit hole once you start going down. There's so many different parameters that you could look at.
That's a brilliant answer, thank you very much. Next question on the list is, so sliding on top and bottom layer is likely, I expect, to make up a relatively small amount of the use applications. Can you speak to what might be the effect for sliding on surfaces made up of a stack of layers, i.e. side layer sliding?
Yes, I completely agree. The one of the fantastic benefits of this technology is that you can produce geometries with really complex you can produce parts with really complex geometries. So you'd expect the sliding to occur on surfaces that aren't just parallel to the build direction. We did have a look at side surfaces, but intrinsically side surfaces are quite hard to characterize because they comprise of lots of I guess reentrant or overhanging features, which means typical like line of sight metrology methods are not able to grasp a full picture of these side surfaces. But we know these side surfaces are a lot more like top surfaces compared to bottom surfaces. So we thought if we could perform this work on top surfaces, we could almost expand that out, extrapolate that out to what might happen with side surfaces or surfaces orientated non-parallel to the powder bed.
Thank you very much. Still got quite a few to get through. Next question was, did you consider including both PTFE and MS2 or graphite to improve friction and wear resistance together?
That's a great question. That's something that we didn't have scope to do, just mainly because of time constrictions, but it's something that I would love to do in the future, do a proper design of experiments to assess like the combination of different solid lubricants. Also, we looked at adding these fillers in just one sort of loading ratio. It'd be great to explore adding them in higher ratios, and it'd be really interesting to see if we can get desired friction and wear properties by tailoring the amount of solid lubricant that we add. And I think that would add some really interesting real world benefits. Also, it'd be great to look at different materials as well, different fillers outside of the three that we looked at. But I think it's a really interesting area in which this research could go down in the future.
Thank you. So do you have sort of future plans to carry on the solid lubricant work?
Not as of yet, no. Just finishing writing up my thesis at the minute, so that's the main focus. But yeah, we'll see, I guess.
Next question, do you see any real world applications of these lubricant mixed nylon 12 powders for part production?
I've not seen any specific Oh, actually, there is a company that does produce sort of nylon 12 powders for laser sintering with a tribology focus, and not quite sure what are in their materials, but they have they they advertise their material as being particularly apt for friction and wear applications in industry. So I do think there is a potential for these materials to, this work to be developed. We are seeing the application of nylon 12 parts in general growing and growing each year for various different applications. So I think the scope is definitely there. The materials I tested were very processable, which is a good sign. But I think it's about just establishing for like a more solid base, and letting companies then use the knowledge gained for their individual applications.
Great, thank you. The next question in comments on a nice presentation, thank you. Please could you comment on how you measured the wear rates? Notice you plotted instantaneous specific wear, and how did you find this value since the contact spot size will change with time?
Yeah, so during running in, when I think that's the graph referring to, we carried out interrupted sliding tests and characterized wear via mass loss measurements. But typically we calculated wear rates by evaluating the wear scar geometry post testing. And that was in the steady state sliding analysis and the solid lubricant work too.
Next question asks, did you consider any other base materials other than nylon 12? And if you did, what difference did you find in the roughness?
So yeah, my work was all focused around nylon 12 just because it's so widely adopted within. It's just the most widely adopted material, and nylon 12's great because it's really nice to process, which and what I mean by that, it melts and crystallizes at the right temperatures, whereas a lot of polymers don't tend to have those thermal characteristics to make them processable. So a lot of the work that we see is related to nylon 12, and one great way to, I guess, unlock more benefits of nylon 12 is to add functional fillers. So that was the reason why the solid lubricant work was motivated, and I think more generally we see that as well with people adding antimicrobial fillers in as well. Glass beads to improve strength, carbon fiber as well. So yeah, nylon 12 really seems to be a solid base polymer for a lot of laser sintering work.
That's brilliant, thank you. I think this will probably be our last question. Did you only use solid lubricants or any liquids as well?
So with the process, because we added in the solid lubricants into the powder, you have to make sure that's in solid particulate form. So even the size of the solid lubricants, we need to make sure we control. So typically between 5 and 10 microns, and that's so we're processing powders. I don't imagine powders with liquids would spread very well and process very well. So yeah, we're limited to focusing on solid lubricant particulates.
Thank you. We've had one last question come in, which I'll just sneak in. It said, did you try any chemical smoothing?
I didn't try any chemical smoothing as part of this work. That was mainly to assess the surface and tribological properties of parts as built, so produced. Because ideally companies want to go from taking the machines out of taking the parts out of the machine and then putting them in the systems rather than incurring too many additional processing steps. I do think it'd be really interesting to have a look at chemical smoothing, and I know there's quite a lot of work going on around that at the minute to promote the benefits of chemical smoothing, because I think in the past it's been done, but I think the chemicals that you employ are quite harsh. So yeah, I think that would be interesting for future work as well.
That's great. Thank you very much. That is the end of our questions. So thank you once again, Kieran, for your really interesting presentation. Great amount of work gone into that over the last few years. All the best to you in the last bit of writing up your thesis. I'm sure that if anybody who has been watching has any more questions or any more thoughts of future work for you, you'd be more than interested to receive any emails. I know your email address was on your slides. I think it was.
Yes, it was.
Yeah. So it was, yeah. Lovely, thank you. Okay, so that brings this webinar to an end. Our next webinar is on Friday the 5th of April, so we'd love you to be able to register and come along to the next one. We'd also really like any more volunteers for further talks to approach us. We can only run these when we have great volunteers from really interesting presenters, so that would be really good if you could get in touch with us if you'd like to present. We've also got upcoming closing date for nominations for the Tribology Bronze Medal. Candidates can self-nominate, but you'll need a referee to support your application. So more information on the Bronze Medal can be found on the IMechE website under the Tribology group pages. And that's it for our Tribology webinar today. So thank you very much for listening.